In essay number 2 for unit number 4, first I will quickly talk about tubuloglomerular feedback and how that works, and that affects the GFR rates. So it all happens here in the macula densa cells. If we have an increase in sodium chloride, then we see adenosine, which will vasoconstrict the afferent arteriole, which is this one here, it's that front one, which will decrease our GFR. And then if we see a decrease in our sodium chloride, then we'll see nitric oxide appear, which will dilate that afferent arteriole, which will increase the GFR. So that's just pretty simple tubuloglomerular feedback. But next we're going to talk about the RAS system, the renin, angiotensin, and aldosterone systems. So it all occurs from osmoreception, which is the osmolarity receptors in your body, and through baroreceptors, which are the same ones that are in the carotid arteries that affect the heart rate. So we'll talk through the RAS system first. So it is happening in the kidneys where we have the release of renin, which is that first R. Renin will go to the liver, which activates angiotensinogen, which activates angiotensin II, which will go to the lungs, which affects the ACE. And from there, we have, I wrote really small here, angiotensin 1, which will affect aldosterone, it will constrict the vessels, and it will affect ADH. So we're going to go back and talk about ADH here quickly. So ADH is the same as vasopressin, and vasopressin kind of describes what that means, where it constricts vessels, it presses on vessels. So vasopressin or ADH will affect the aquaporin. Which is equal to a decrease in urine concentrations because there's more water in the blood. And that's pretty simply the RAS system and the tubuloglomerular feedback. In this final part of the essay, is used to first establish and then maintain the medullary concentration gradients, and then how that gradient and ADH work to excrete different concentrations of urine. So when we move out of Bowman's capsule and head down, this is where much of the water is released out. And so these are all in units of milliosmolar also. Milliosmoles per liter. And so as we start moving down, we start to get this increase in the concentration. But as we move up the ascending, we'll skip this loop of Henle for 1 second. As we move up the ascending, we have sodium chloride coming through channels here. Everywhere where I'm making dots, there's little channels. And we have sodium chloride leaving to reestablish the gradient. So here in the loop of Henle, we have almost no water and a lot of salt because the salt has not left yet because it leaves as it moves up. So we have a really strong concentration gradient here. Because of that gradient, we we maintain the medullary concentration. And it's all done here because nothing really happens here. All of the movement in and out is in the ascending and descending tubules. And when that happens, as things move up and through, and this would be the collecting duct would be here. We'd have that juxtamedullary coming in from this side. We have a lot of different kind of concentrations that can come through. If we don't let as much water out, then the concentration of sodium down here will change and we won't push as much out. And so we'll have a much more concentrated urine come out. It'll be a lower volume and more concentration. Whereas if we retain more water and we move it through and out, then what comes out here will have a higher volume and will be less concentrated. Those two are an inverse relationship. Will determine what our urine looks like. The more concentrated the urine is, the more yellow it typically is, and vice versa. The more urine we have, usually it's typically a little bit clearer, and that's just because more water is there. And ADH can also help do this. ADH is known as a diuretic, and that can help us to release more out in our urine. But that is how that works.